quiet beginning in the vastness. Space doesn't need permission to be vast. You're about to hear the kind of facts that don't make it into school books, but stay with you forever. Let your mind go quiet now, and let the universe start talking. Scale of the universe. Grains of sand versus stars. They say Earth's beaches hold more grains of sand than a person could count in 1,000 lifetimes. Every coast, every desert, every corner of the world where sand settles. Trillions upon trillions of tiny particles covering the planet. And yet, if you were to take every single grain from every single beach and desert on Earth, the stars would still outnumber them. Not by a little, but by galaxies. Across the observable universe, there are estimated to be more than 100 billion galaxies. And each of those galaxies contains hundreds of billions of stars. Just our own galaxy, the Milky Way, holds around 200 billion. Multiply that across the full span of what we can observe, and the total number of stars rises into the septillions. That's a number with 24 zeros. Not theories, not guesses, just scale. Quiet, overwhelming scale. And yet, most of those stars won't ever be seen by the human eye. They sit too far, or too dim, or behind clouds of interstellar dust. Some are so distant that their light hasn't even reached us yet, and may never will. But they're still there, burning silently. Some have been burning longer than our solar system has existed. Some have already gone out. What this means, at its core, is that nothing about our position is central. There is no middle of the universe with Earth planted firmly inside it. We are not surrounded by a small neighborhood of stars. We are buried deep within something so large, no direction points to the edge. In every direction we look, the sky stretches farther than our instruments can reach. And beyond that, it keeps going. Not just outward, but backward in time. Light from the most distant stars and galaxies takes billions of years to arrive, meaning we're not just looking far, we're looking into the past. A past filled with more stars than all the sand this world has ever touched. And yet, here we are, on one planet, among just a few we've explored, orbiting one star out of all the rest, a single grain of dust floating in something beyond counting. There's no need to solve it. Just know this: the night sky you see is only a sliver of what's really there. The rest stretches on, quiet, endless, and real. Sun's size versus Earth. Light-year comparisons. If you could set the Earth beside the Sun, you wouldn't be comparing two worlds. You'd be comparing a speck of dust to a blazing cathedral of fire. The Sun isn't just larger than Earth. It's so vast that over 1 million Earths could fit inside it and still leave space around the edges. The scale isn't symbolic, it's real, and it's measured, not guessed. The Sun holds 99.86% of all the mass in our entire solar system. Every planet, moon, comet, asteroid, satellite, combined, barely adds up to a fraction of the Sun's weight. It's a furnace of hydrogen and helium, burning at its core with temperatures around 15 million degrees Celsius. And somehow, this overwhelming force has been doing that for more than 4.6 billion years, without burning out or falling apart. Every second, the Sun converts 600 million tons of hydrogen into helium through nuclear fusion. That process releases energy, enough to supply Earth with all its light and heat from a distance of nearly 93 million miles. Even at that distance, our skin can feel its touch, our crops depend on it, our climate orbits it, and yet, that 93 million miles is nothing compared to what lies beyond. When we talk about distance in space, regular numbers break down. Miles and kilometers stop being useful. That's where the light year comes in. A light year isn't time, it's distance. how far light can travel in one Earth year. That comes out to nearly 6 trillion miles. And even that number, massive as it is, only covers the first few steps beyond our solar system. The nearest star beyond the Sun is Proxima Centauri, roughly 4.24 light-years away. If you were to fly there in a modern spacecraft moving at the speed of the fastest probe we've ever launched, Voyager 1, you'd still need over 70,000 years to reach it. That's the kind of scale we're dealing with. A trip to our nearest neighbor takes longer than all of recorded human history. We measure things in light because it's the only thing fast enough to reach across the dark. When you look at the moon, you're seeing it as it was 1 second ago. The sun? That's light that left 8 minutes earlier. And the stars that fill your night sky. Some of those rays have been traveling for thousands, even millions of years, crossing empty voids, slipping past galaxies, bending around gravity wells, just to land on the back of your eye. It's easy to think of Earth as the center of something, but when you weigh it against the sun, when you count its size next to the scale of a light year, the reality becomes quieter and clearer. We're not big and we're not fast. We are local passengers on a journey carried by forces much greater than ourselves, surrounded by light that's older than our species, Milky Way structure and our place in it. We live in a galaxy shaped like a disk, but it's no simple spinning circle. The Milky Way is a massive barred spiral galaxy with arms made of stars, dust, gas, and invisible matter stretching outward like curved spokes on a broken wheel. From edge to edge, it spans over 100,000 light-years, a scale that breaks away from instinct. Yet, even with all that size, we occupy no grand position. Our solar system sits quietly on the inner edge of a minor arm called Orion's Spur, nestled between two larger arms, as unremarkable as a raindrop in a storm. If the Milky Way were shrunk to the size of North America, our entire solar system would fit comfortably inside a coffee mug resting somewhere in Kansas. That's how small our neighborhood is compared to the whole. We are not near the center. We're not on the edge. We're somewhere in the middle of the middle, carried along as the galaxy rotates. A slow turn that takes about 230 million years to complete just one orbit. And yet, the galaxy isn't still. The arms rotate, yes, but they're also rippling. Like waves in water, each star, each system, is moving under the push and pull of gravity. Some of the arms are dense and active, full of starbursts and glowing gas clouds. Others are more settled, quieter, with older stars burning out like coals at the edge of a dying fire. Our solar system currently drifts through one of these calmer zones, but it wasn't always this way, and it won't stay that way forever. The Milky Way is not a solid structure, it's dynamic and layered. There's a central bulge packed tight with older stars, a flat disk containing spiral arms, a thin disk where most of the younger stars are born, and an extended halo of ancient stars and clusters circling loosely around it all. Beyond that, there's a cloud of dark matter we can't see, but we know it's there, holding the galaxy together like invisible glue. And we're not alone. There are over 150 globular clusters orbiting the Milky Way, dense balls of stars, like bright seeds spread around its outskirts. There are satellite galaxies too, smaller ones like the Large and Small Magellanic Clouds, trailing behind like cosmic companions. The Milky Way is not a solitary traveler. It's part of a community, a group of galaxies moving together in space known as the local group. Everything you've ever known, every history book, every family, every word that's been spoken, has happened on a tiny planet orbiting a single star, in a quiet corner of this spinning disk. And while we often look outward with awe, what surrounds us is only one of billions of galaxies. Still, the Milky Way is home. Not because we chose it, but because it's the only one we've ever known from the inside. Black hole at the center of the Milky Way. Sagittarius, a star. At the center of our galaxy, hidden behind clouds of gas and dust, there's a gravitational anchor, a point so heavy, so compact, that light itself cannot escape its pull. It's called Sagittarius A star, and it's not a theory, it's a confirmed object, a supermassive black hole, roughly 4.3 million times the mass of our Sun, packed into a space no larger than the orbit of Mercury. It doesn't shine. It doesn't glow. You won't see it from your backyard or through any backyard telescope. But it's there, and we know it's there because of how it moves the things around it. Stars near the galactic center don't drift slowly like leaves in a stream. They whip around it at incredible speeds, following tight elliptical paths. Some complete their orbits in as little as 16 years. That kind of motion takes an immense force, one that can only come from something incredibly massive and incredibly small. But Sagittarius A star isn't just a cosmic vacuum cleaner, it's mostly quiet. For now, it doesn't feed constantly. In fact, it's relatively dormant compared to the supermassive black holes in the younger, more active galaxies. But when it does pull matter inward, it flares. Gas and debris spiral into its gravitational well, heating up, releasing energy, then vanishing past the event horizon, a boundary from which nothing, not even light, can return. The event horizon is not a surface. There's no shell, no wall, no crust. It's a region where space curves so extremely that every possible path leads inward. Once matter crosses that invisible edge, its future becomes unchangeable. There is no pause, no reversal, only descent, toward something we can't measure, can't reach, and may never fully understand. The presence of Sagittarius A star holds the Milky Way together. Without it, the galaxy's core would slowly unravel. Its gravity binds not just nearby stars, but the broader central structure, regulating orbits, anchoring movement, creating stability in chaos. In a sense, it's both destroyer and organizer. Destructive in the way it consumes. Constructive in the way it shapes the dance of stars around it. And even though it's hidden from view, we've captured its fingerprint. In 2022, radio telescopes acting in unison gave us the first real image of the matter swirling around its edge. A blurry but unmistakable ring of energy encircling darkness. It wasn't clear like a photo, it was raw, filtered data transformed into the closest thing we've ever had to a portrait of our galaxy's beating heart. To think that right now, at the very center of everything we call home, there is an object that bends space and time, not metaphorically but physically. Not only does it influence the motion of stars, it slows time itself in its immediate region. If you were to approach it, time for you would crawl, while the universe outside would race ahead. And it just sits there, waiting, quiet, heavy, permanent. The galaxy turns around it and we move with it, never knowing what it's thinking, if it can think at all. But still, it's there, the darkest thing in our sky and the most dependable. Introduction to Cosmic Distances and Measurements. The human brain is built for small things. Inches, feet, maybe miles when we push. We're good at remembering the length of a football field, the distance to a grocery store, the hours it takes to drive to another city. But when we leave the planet, those numbers collapse. They lose their meaning. Space doesn't respect our rulers. It demands new tools that match its scale. In astronomy, distance isn't just about how far. It's about how long light takes to get from one place to another. And since light is the fastest thing that exists, it becomes our standard of measurement. A light second is the distance light travels in 1 second, around 186,000 miles. That's about 3/4 of the way to the moon. A light minute takes you to the sun, A light hour gets you beyond the solar system. But the real language of space begins with the light year, a full trip for light in a single Earth year. That's nearly 6 trillion miles, and even that number only scratches the surface. Some of the stars you see at night are just a few dozen light years away. Their light left in the 1990s or early 2000s. Others, far fainter, left their mark before your grandparents were born. A single galaxy can be millions or even billions of light years distant, meaning its light has been on the road since before Earth had complex life. And yet that light still arrives, quietly, without warning, hitting the same retinas that read street signs and alarm clocks. We also use astronomical units, or AUs, when dealing with things inside our own solar system. 1 AU is the distance from Earth to the Sun, about 93 million miles. Mercury orbits at roughly 0.4 astronomical units. Mars sits at 1.5. Neptune, the farthest planet, cruises at nearly 30 astronomical units. These numbers help us make sense of the local neighborhood without constantly reaching for trillions. But the moment we leave the system, AUs fall apart. They're too small for what's ahead. Then there's the parsec, short for parallax arc second. It's based on geometry and angles, using Earth's movement around the Sun to calculate how distant stars shift against the background sky. 1 parsec equals about 3.26 light years. It's not used in casual speech, but it shows up often in serious measurements. Nearby star clusters might be a few hundred parsecs away. The center of the Milky Way sits roughly 8,000 parsecs from Earth. What makes all this difficult isn't just the size, it's the silence. These distances don't shout. They don't announce themselves. They stretch quietly across emptiness, forcing us to invent units just to grasp their shape. Light years, AUs, parsecs, they're not interchangeable. They're different keys for different doors. But here's the simplest truth. When you look up at the night sky, you're never looking at where anything is right now. You're looking at where it was. The farther the object, the older the light. Some of what you see no longer exists. Some of it hasn't even arrived yet. Space is measured in distance, yes, but also in delay. Everything is behind schedule. Every twinkle is a time capsule. Every star a delayed message sent across impossible lengths, finally received without a sound. The known universe is only approximately 5% visible. Everything we've ever studied in space, every star, every galaxy, every planet, every speck of dust, makes up less than 5% of what actually exists. Not 5% of the solar system, not 5% of one region, 5% of the entire universe. The rest we can't see. Not because it's too far or too faint, but because it doesn't interact with light at all. It's invisible in the most literal sense. The things we call visible matter, atoms, molecules, all the familiar elements, are not the bulk of creation. They're just the surface, a thin crust on something vastly deeper. This 5% includes every known object that reflects, emits, or absorbs electromagnetic radiation. That means it includes every star we've cataloged, every nebula we've imaged, and every galaxy whose spiral arms stretch across telescope lenses. But the remaining 95%, what we can't directly observe, makes up the true weight of the cosmos. There's a kind of humility in knowing that most of what surrounds us has never been seen. Not by cameras, not by sensors, not by mathematical modeling alone. The fabric of the universe is held together by substances and energies we've only detected through their effects, not through their appearance. They don't glow, they don't scatter, they don't behave like any material we've studied on Earth. And yet they are there, pressing, bending, shaping everything around them. When we point our most advanced telescopes at distant clusters of galaxies, the light we capture shows only part of the picture. The visible parts don't explain the way those galaxies move. They spin too fast. They hold their shape when physics says they should unravel. The gravity required to keep them intact must come from something else, something massive but unseen. And that invisible mass appears to dominate the structure of the universe on every scale. This hidden matter doesn't just exist between galaxies. It weaves through and around them, creating scaffolding for the visible universe to build upon. It forms massive halos around galaxies, fills the vast space between clusters, and seems to guide the formation of cosmic structures in a way that visible matter alone could never do. Without it, the stars would drift apart like ash in the wind. With it, they move in synchronized silence. It's unsettling in a way. Most of reality isn't made of the things we understand. The familiar laws, the ones that govern chemistry, heat, magnetism, operate on only a sliver of the whole. The rest follows rules we haven't fully uncovered. And even when we try to model this invisible realm, we're often working backward, observing strange behavior, then asking what could cause it, rather than detecting a substance directly. It's like studying wind by watching how trees bend. Still, what we do know is this: our tools have limits. Our sight, our instruments, our methods, they reveal what they can, but much remains out of reach. The truth isn't always in what we see, but in what we sense. Movement without a mover. Curves without contact. Forces without form. The universe is built on a foundation that doesn't care whether we can see it or not. It just is. And that silent, invisible majority remains the most dominant presence in existence. What dark matter does without speculation. Dark matter has no light, no color, no texture. You can't feel it, you can't reflect it, and you can't catch it in a bottle. But you can see what it does. Its effects ripple across the universe like invisible fingers shaping the cosmos from behind the curtain. Wherever there are galaxies, there's dark matter nearby, threaded through them, wrapped around them, stretching out beyond what our eyes can reach. What dark matter does, above all, is hold things together. Not in theory, but in force. When astronomers measure the speed at which stars orbit the centers of galaxies, the numbers don't add up. The visible matter, the gas, the dust, the stars, doesn't produce enough gravity to account for the way those galaxies spin. At the edges, where things should be drifting apart, the stars are still locked in place, orbiting faster than expected. Something is pulling on them, something with mass but without light. This isn't a rare phenomenon. It happens in every galaxy we've studied. It's consistent, predictable. The unseen matter forms massive halos that extend well beyond the visible edge of a galaxy, like a hidden skeleton holding its shape. And it's not just limited to individual galaxies. Whole clusters, collections of hundreds or thousands of galaxies, also show signs of being bound together by more gravity than their visible matter can explain. Dark matter doesn't clump like regular matter. It doesn't form stars. It doesn't gather into planets or moons. It doesn't burn or freeze or collapse in the way atoms do. Instead, it forms vast, smooth distributions. It passes through ordinary matter and itself without friction. When two galaxies collide, their dark matter halos slide past one another, while the visible gas and stars interact, clash, and sometimes even slow down. It's as if dark matter is watching the chaos from a distance, present but untouched. Its presence also leaves fingerprints in the cosmic microwave background, the leftover glow from the early universe. The patterns in that ancient light reveal tiny fluctuations, bumps in density, that grew into galaxies over time. Without the gravitational influence of dark matter, those bumps wouldn't have had enough pull to grow. The universe as we know it, structured, clumped, star-filled, could never have formed in the time available. Another one of dark matter's behaviors is gravitational lensing. That's when the gravity of massive objects bends light from objects behind them. The stronger the gravitational field, the more the light warps. We've seen light from distant galaxies stretched and distorted by dark matter sitting in front of them. Mass we cannot see, shaping the path of photons across space. It bends the light, not because it glows, but because it exists with weight. It's not a ghost or a guess. It's a framework that allows the large-scale structure of the universe to exist in the form we observe. Without it, spiral arms would unravel, galaxy clusters would fly apart, and the early universe would have stayed too smooth to evolve into anything interesting. It doesn't ask to be noticed. It simply performs its role without pause. So even though we may not yet know what dark matter is, we know what it does. It sustains structure, it deepens gravity, it guides growth. And it does so invisibly, constantly and everywhere, shaping a universe that remains visibly incomplete without it. How galaxies stay together. Galaxies are not held together by stillness. They're spinning, moving. Every star, every cloud of gas, every particle of dust, constantly in motion. In some cases, stars orbit the center at hundreds of kilometers per second. You would expect, by those speeds alone, for galaxies to fly apart like shattered wheels. The force of that motion should overwhelm the pull of gravity from the matter we can see. But it doesn't. Somehow, these enormous systems, some of them stretching over hundreds of thousands of light years, hold their shape. And they've done so for billions of years. The stability of a galaxy isn't a coincidence. It's not the result of some delicate balance that just happened to work out. It's structural, it's physical. Something unseen is adding weight, pulling harder than what our visible mass can account for. This extra pull doesn't just keep galaxies together. It gives them their form, their rotation curves, their very ability to stay intact across time. Take spiral galaxies as an example. They have arms that curl outward from a dense central bulge. If the only gravity at work came from the visible stars and gas, those arms would lag behind the rotation. The outer regions should rotate more slowly, much like the outer planets of our solar system move slower than the ones closer to the sun. But observations show that stars on the outer edges of galaxies are moving just as fast as those near the center. That speed, at those distances, defies the expectations of normal gravity. Something else is keeping those stars in orbit, something providing additional mass far beyond what we can detect directly. This invisible framework doesn't clump into stars or settle into disks. It exists in a halo, an extended region of gravitational influence that surrounds the visible parts of a galaxy. These halos can be 10 times larger than the galaxy itself. They don't radiate heat, they don't absorb light, but they're there, shaping the motion of everything inside. Even in elliptical galaxies, those more rounded, three-dimensional clouds of stars, the same pattern holds. The stars move with a speed that implies far more mass than can be accounted for by the matter we can see. And when galaxies gather into clusters, the effect becomes even more obvious. There isn't enough visible material to keep them bound together. The velocities of the galaxies would send them drifting apart if there wasn't an unseen glue working in the background. This force isn't erratic, it's not selective. It operates with the same consistency across vastly different systems, from dwarf galaxies to giants with trillions of stars. And while the mechanisms of normal gravity apply, the inputs are incomplete. When calculations are run based solely on visible mass, the numbers fall short. When the hidden mass is accounted for, the models hold together. What's even more telling is how these unseen forces guide interactions. When galaxies merge, their stars rarely collide, but their invisible halos do. These interactions affect how long galaxies take to combine, how their structures deform, and how new star formation is triggered. The unseen influence doesn't just preserve, it also directs. It reshapes, slows, or accelerates evolution on galactic scales. So, when you look at a galaxy, any galaxy, know that you're not seeing the whole picture. You're only seeing the parts that glow. Beneath that glow is a vast and silent structure that keeps the stars bound, the shape intact, and the entire system stable over cosmic time. It is what allows galaxies to endure, not for centuries, not for millennia, but across eons, unchanged by the forces that would otherwise tear them apart. Cosmic expansion and dark energy's strange role. There was a time when we thought gravity would win, that after the initial burst that launched the universe outward, everything would slow down. Galaxies would pull on one another, clusters would tighten, and eventually, the entire cosmos would either collapse in on itself or drift into stillness. But what's actually happening isn't slower, it's faster. The space between galaxies isn't just stretching, it's accelerating. And the deeper we look, the stranger that truth becomes. This expansion doesn't come from within galaxies. It's not the stars themselves flying apart. The structures inside galaxies are held together tightly by gravity. Instead, it's the space between them that's growing. The kind of growth that doesn't need motion in the traditional sense. It's not like a galaxy is flying away like a rocket. It's more like the fabric of space itself is unfolding between them, making the distance greater over time, even without movement from the galaxies themselves. Now, here's where the strange part begins. What's causing that expansion to speed up isn't visible. It's not heat, mass, or pressure. It's something completely different. Something with no texture or shape, yet it fills all of space. We call it dark energy, but the name doesn't describe what it is. It only hints at what it does. Dark energy isn't pushing in the usual way. It acts more like a negative pressure, a property that causes space to expand instead of contract. It works against gravity, not by tearing things apart directly, but by causing the very space in which they exist to stretch. The farther away something is, the more space there is between us and it, and the more dark energy has room to act. That's why galaxies beyond a certain distance appear to recede from us faster and faster, even though they're not accelerating in the traditional sense. It's space itself that's stretching. If that sounds counterintuitive, it's because it is. It breaks the rules we're used to. It's not like wind or magnetism or mass. It's a property of the vacuum, a force with no source in matter. And yet, it makes up nearly 70% of everything in the universe. It doesn't collect or scatter. It doesn't change the rotation of planets or the heat of stars. It only affects the large-scale structure of space, and only becomes noticeable when that space stretches far enough. What's even more unusual is that dark energy isn't diluted as the universe expands. With ordinary matter, spread it thinner, and there's less per volume. But dark energy doesn't seem to behave like that. It maintains a constant presence, no matter how much space increases. In fact, the more space there is, the more of it appears. That means expansion creates more room for expansion, a kind of runaway growth that leads to a future very different from what was once expected. And this expansion isn't local, it's everywhere, between galaxies, between galaxy clusters, across the deepest voids. It operates uniformly, not favoring one region over another. If left unchecked, it will continue. Not until the galaxies stop interacting, but until they can no longer even see one another. The light from distant galaxies will stretch so far it will vanish from view completely. Future observers, billions of years from now, may live in isolated patches of space with no knowledge that other galaxies ever existed. This isn't something we feel. It doesn't weigh on our skin or push against our lungs, but it shapes the fate of everything on the largest possible scale. It won't shatter stars or extinguish life, but it will decide how much space there is to live in and whether any of it stays connected. Dark energy doesn't roar. It whispers across distance, and in that whisper the universe is being pulled apart, slowly, steadily, without a sound. Hints that dark energy might be changing. When dark energy was first detected, it seemed steady, quiet, uniform, a background property of space, untouched by time. But the deeper we look and the further back we reach, the more that stillness starts to ripple. Subtle shifts in the data hint that dark energy might not be fixed after all. It may have a past. It may even have a future of its own. What we see today is an accelerating expansion, space stretching faster than before. That's what led to the idea of a constant dark energy in the first place. But the light from distant galaxies doesn't just show where they are. It shows where they were and how they moved across billions of years. And when we line those stories up, layer after layer, something unexpected begins to show. The expansion rate hasn't been entirely smooth. There are tiny inconsistencies between different measurements. Some of the light from older galaxies suggests a slower acceleration than we observe closer to home. It's like watching a clock that ticks faster as it ages. The question is whether that's an error in how we're watching, or a signal of how the clock itself is changing. The numbers don't scream, they whisper. Tiny differences in the way distant light stretches. Minor fluctuations in how galaxies formed at different epochs. Patterns in the cosmic microwave background that don't quite match today's pace. All of them, on their own, could be brushed aside. But together, they start to tug at the edge of certainty. If dark energy is shifting, it means space is more complex than we thought. It might not just contain energy, it might produce or release it in stages. Perhaps the fabric of space was more restrained in the past, and only recently began to accelerate more aggressively. Or perhaps the effect is temporary, building towards something else. If that's true, we're not just watching expansion. We're watching a phase in a larger cycle we don't yet understand. There's also the possibility that what we call dark energy isn't one thing at all. It may be a label covering multiple processes, some constant, some evolving, some bound to matter, some free from it. It may not be energy in the traditional sense, but rather a reflection of how space-time itself is reshaping. These aren't just academic questions. If dark energy grows stronger, the expansion of the universe will accelerate even faster. That would stretch galaxies so far apart that the sky would eventually turn dark. Not because the stars died, but because their light could no longer reach us. Worse still, if dark energy becomes unstable, it could disrupt matter itself. In some scenarios, even atoms would be torn apart in the distant future. On the other hand, if dark energy is fading, expansion might slow down. The universe could drift toward balance, neither collapsing nor accelerating endlessly, a kind of silent standoff between matter and the emptiness around it. That outcome would leave the room for new structures to form, galaxies combining, clusters evolving, without being torn from each other too quickly. For now, the changes are too slight to claim certainty, but they're enough to keep asking, enough to keep refining the instruments, reviewing the maps, rechecking the light. Because if dark energy can change, the entire fate of the universe hangs on its behavior. It wouldn't just affect the cosmos, it would decide it. And so, we watch the quiet force behind expansion, not with panic, but with patience, waiting to learn whether the force that pushes the universe apart is locked into place, or still writing its own story, line by silent line across the deep fabric of time. The Great Attractor. Pulling our galaxy at 600 kilometers per second. The Milky Way isn't floating quietly. It's not suspended in stillness or drifting aimlessly through space. It's moving fast. Our entire galaxy, with all its stars, gas, planets, and dark matter, is racing through the cosmos at over 600 kilometers per second. That's more than 1.3 million miles per hour, and we're not heading in a random direction. We're being pulled, dragged relentlessly toward something vast and largely unknown. That something has a name. We call it the Great Attractor. It isn't a single object like a star or black hole. It's a region of space so dense with mass that its gravitational pull is warping the motion of entire galaxy clusters. The Great Attractor lies within a section of the sky we can't even fully see, hidden behind the crowded plain of the Milky Way, in an area astronomers call the Zone of Avoidance. But even though it's hard to observe directly, we can detect its effect. Galaxies across hundreds of millions of light years are all streaming in one general direction, toward it. This isn't a small-scale disturbance. The pull of the Great Attractor is powerful enough to redirect the motion of superclusters. Not just individual galaxies, but entire collections of galaxies, thousands of them, are converging toward this gravitational basin. Our local group, which includes the Milky Way and Andromeda, is just one part of a much larger structure known as the Laniakea supercluster. That supercluster, in turn, is being pulled along with many others toward this gravitational anomaly. What's remarkable is that we don't fully know what lies at the heart of it. We know it involves a collection of galaxy clusters, including the massive Norma cluster, and perhaps others that are still obscured by gas and dust in our line of sight. But we don't know the full mass, the complete shape, or the final destination. It's like feeling the tug of a current in a deep ocean, without knowing where the tide began or where it's pulling us next. The pull is steady, not sharp or chaotic, but firm, like gravity on a planetary scale, stretched out to cosmic proportions. Every object nearby, every galaxy within this immense region, feels the same influence. The motion isn't caused by momentum alone. It's a directional movement, one guided by the invisible hands of gravity acting over hundreds of millions of years. And this movement isn't optional. There's no resistance strong enough to stop it. No force of propulsion, no stellar mass, no local gravity well that can override the pull. We're part of the flow, our galaxy caught in a vast river of motion, carved out by density and time. Over the years, scientists have mapped out the velocity field of surrounding galaxies using their redshifts and relative positions. What they've found is convergence, a massive central area where galactic paths bend inward. That area lines up with the Great Attractor. It acts like a dip in the cosmic landscape, a valley so broad and deep that everything around it tilts slightly toward its center. Even though we can't see the whole picture, the pattern is undeniable. We are moving because something is making us move. And it's not just us, it's the architecture of this entire region of the universe, reoriented by a pull that isn't letting go. What's humbling is that our galaxy, with all its billions of stars and its central black hole, is barely a participant. It's being carried like a leaf in a slow-moving flood toward a destination that remains shrouded in both distance and mystery. But the motion is real, it's measurable, and it means that even on the largest possible scale, we're not in control. We're part of something wider, deeper, and still unfolding. Always moving, always pulled. toward something we can't yet see, but can no longer deny. Tidal tails: what happens when galaxies collide. Galaxies are not static islands. They are travelers, huge, spiraling structures made of hundreds of billions of stars, all moving through space. And sometimes those paths cross. Not in sudden crashes like cars on a highway, but in long, slow, gravitational encounters that stretch across hundreds of millions of years. These collisions don't look violent in the way we understand violence. They're graceful, even quiet. But the effects they leave behind are anything but subtle. When galaxies begin to interact, the first thing that happens isn't impact, it's distortion. Their shapes begin to warp as gravity reaches across the void between them. Long before the cores touch, the outer regions feel the pull. Stars are lifted out of their orbits. Gas clouds are twisted and dragged. The elegant spiral arms lose their balance, and the galaxies begin to stretch one another like pulled thread. This process creates what are known as tidal tails, vast, sweeping streams of stars and dust flung outward into space. These tails can extend for hundreds of thousands of light years, tracing the motion of the interaction like trails left in water. They're not random. They form from the outer edges of galaxies where gravity has a looser grip. As two galaxies pass near each other, gravitational forces pull on the stars unevenly, creating a tension that draws material outward in opposite directions. One tail might arc backward, following the path of the smaller galaxy. Another might fan out ahead, thrown forward like a flare. Some tails remain narrow and bright, while others diffuse into complex webs of scattered light. Their shapes depend on the angle, speed, and mass of the colliding galaxies. No two look alike, but all tell the same story: that something enormous just passed through. Inside these tails, the chaos isn't just visual, it's physical. Gas clouds are compressed as they're dragged and twisted. That compression leads to new star formation, igniting young, hot stars in regions that were once quiet. So, while a tidal tail may look like a trail of debris, it's also a nursery, a place where the disturbance breathes life into something new. Stars that form in tidal tails are often isolated, far from the galactic core, and their orbits become unique, stretched by the same forces that created them. In some collisions, the tidal tails become bridges. The galaxies may pass so close that they form a luminous strand of stars connecting them, like a hand reaching out and grabbing hold. These stellar bridges can exchange material between galaxies, changing their structure forever. Some tails will fall back in, pulled home by gravity. Others will be lost to the void, drifting freely through intergalactic space. Tidal tails also reveal the hidden nature of galaxies. Their formation isn't dictated only by the stars and gas we see. They respond to the total gravitational field, including dark matter. The way a tail curves, its reach, and its coherence all reflect the shape and mass of the invisible halo surrounding the galaxy. In this way, tidal tails are more than leftovers. They're fingerprints of the galaxy's entire structure, visible clues to invisible forms. And even after the galaxies merge, after the cores combine, after the original shapes are erased, those tails can remain, sometimes as faint arcs of light far from the new galaxy's center, sometimes as permanent streams of stars wrapped into orbit like ghostly ribbons. In the end, they mark the path that was taken. They tell the story of where the galaxies came from, how they met, and what they left behind. To see a tidal tail is to witness memory frozen in light, not the memory of a single star or system, but of entire galaxies caught in motion, reshaped by forces that operate on unimaginable scales. These tails don't form quickly. They don't disappear easily. They are the echoes of encounters too vast for any one lifetime, and yet they remain, glowing quietly, reminders that even in the largest structures in the universe, gravity still knows how to leave a scar. Antennae galaxies, the mice galaxies, and visible collision debris. Some of the clearest evidence of galactic collisions doesn't come from theory. It comes from the sky itself. From two galaxies locked together, stretched beyond recognition, leaving behind streams of stars, shattered shapes, and glowing trails that trace the violence of their meeting. These are not silent events. The light tells the story. It travels across millions of light years to show us what happens when gravity draws two colossal systems into one. The Antennae galaxies, a pair of once separate spiral galaxies now in the process of merging, are among the most iconic examples. Named for the long arcing streams of stars that reach out from the center like antennae, these structures didn't exist before the collision. They were created by it. Pulled outward by tidal forces as the galaxies passed through one another, the stars now form bright, trailing arcs that sweep tens of thousands of light years into space. At the core of the antennae, the collision is even more intense. Dense regions of gas have been squeezed together under gravitational pressure, igniting massive bursts of star formation. These aren't slow-burning stars like our Sun. They're short-lived giants, blue, hot, and fierce, forming by the thousands in compact clusters. Some of these young clusters are so densely packed that they may evolve into globular clusters, ancient, spherical arrangements of stars that orbit galaxies for billions of years. But these bursts don't last forever. As the galaxies continue their violent choreography, the same compression that sparks star formation will also trigger chaos. Supernovae will erupt. Black holes may form in dense regions. And eventually, over hundreds of millions of years, the original shapes will dissolve. Spiral arms will disappear. Disks will flatten. What will be left is one single, irregularly shaped galaxy, scarred but complete. Then there are the mice galaxies. Two long, thin spirals caught in the middle of a close encounter. Their name comes from the extended tails that trail behind them, giving the appearance of two cosmic rodents darting through space. These tails, like those in the antennae, were torn away during the interaction. One tail sweeps back in a graceful arc. The other flicks outward, narrow and fragmented. Each one is made of stars that have been ejected from their orbits, pulled by gravity into elongated paths that reflect the intensity of their collision. But it's not just the tails that tell the story, it's the distortion in the cores. The central bulges of the mice are stretched and warped. Dust lanes cross in irregular patterns. Star formation burns brightly in pockets, like brief fires lit by the friction of movement. The symmetry is gone. What's left is motion, heat, and change. Across both of these systems, the antennae and the mice, the visible collision debris reveals a truth that can't be ignored. Galaxies are not untouched by time. They don't pass through the universe without consequences. The debris trails are the footprints of mass in motion, lines written in light that show exactly how the shapes were broken, where they were stretched, and which stars were thrown out like sparks from a forge. This debris isn't just leftover material. It plays an active role in the aftermath. Some of it will be pulled back in, swirling into new orbits. Some of it will gather into dwarf galaxies, smaller structures born from the scrap of a larger event. And some of it will simply drift, cooling and dispersing, no longer bound to the place it came from. The fate of each piece depends on speed, direction, and gravity's continuing reach. Even from our distant vantage point, we can see it all unfold in stages. The early tug, the first distortion, the meeting of the cores, the flaring of light, and the long decay into something new. These collisions don't destroy galaxies. They remake them. They erase the old architecture and leave something larger, something mixed, something that never existed before. In the chaos of these encounters, galaxies leave behind trails of their own history. Stars that were part of one structure, now flung across another. In the tangle of debris, the record remains. Not written in symbols or language, but in arcs of matter, frozen in time, still visible across the void. They are, in every sense, the ruins and the rebirth of the universe's most massive structures. Andromeda's future collision with the Milky Way, what that really means. Roughly 2.5 million light-years from Earth, there's a galaxy hurtling toward us. Not a rogue object, not a threat from some foreign region of space, but our nearest large galactic neighbor, Andromeda. It's coming straight in our direction at around 110 kilometers per second. And nothing will stop it. Not gravity from nearby galaxies, not friction from space, not time. The Milky Way and Andromeda are on a slow-motion collision course that will end in a union so massive, so reshaping, it will rewrite the structure of both galaxies forever. From this distance, it's hard to picture what that really means. Andromeda is vast, larger than the Milky Way in diameter, with a similar number of stars. Its spiral arms are bright with active regions of star formation. It has satellite galaxies of its own halo, its own black hole at the center. And yet, every second it's drawing closer. Not from a fluke, but from the natural motion of clustered matter over cosmic time. The eventual meeting won't be a head-on crash in the way people think of impact. Galaxies are mostly empty space. The stars within them are so spread out that the odds of two individual stars directly colliding are almost zero. Even when the cores pass through one another, the stars will simply slide past, like dancers brushing sleeves in a crowded room. But the galaxies themselves, their shapes, their balance, their orbits, will not remain untouched. As they approach, their mutual gravity will begin to stretch them. The outer arms will twist, gas clouds will distort, some material will be stripped away, and before they even touch, both galaxies will be visibly deformed. Tidal forces will rise. Streams of stars will begin to form, looping far out into space, and the quiet symmetry of two spirals will give way to the ragged structure of something undergoing transformation. Once they begin to merge, the process will take hundreds of millions of years. They may pass through each other multiple times, pulled back together by gravity each time they try to separate. Each pass will trigger waves of star formation, lit by the compression of gas as it's forced into tighter spaces. New stars will form. Others may be ejected into the intergalactic void. Some entire systems may be flung into elongated orbits around the growing, chaotic core of the merger. Eventually, after the motion settles and the dust cools, what will remain will not be a spiral galaxy. It will be something new, something rounder, thicker, less organized. A giant elliptical galaxy, a product of violence and gravity, built from the cores of both galaxies and bound together by their combined mass. Astronomers already have a name for this future object, Milkomeda. Inside this new galaxy, many of the original stars will survive, but their orbits will be changed. The familiar patterns of the Milky Way's rotation will be lost. The Sun, if it still exists then, will likely be carried into a distant and unpredictable path. Whether Earth survives is another question entirely. By the time the collision begins, around 4 billion years from now, our planet will already be facing extinction from the natural brightening of the Sun. Life, if it still exists here, will have long since adapted or moved on. And at the very center of this new galaxy, another collision will occur. Both the Milky Way and Andromeda contain supermassive black holes in their cores. These two will spiral toward one another, shedding energy through gravitational waves before finally merging into one colossal black hole, larger and heavier than either of the ones that created it. That merger, silent in space, will release ripples through the fabric of the universe that could be detected billions of light years away. But perhaps the most striking truth in all of this is not the violence or the scale, it's the patience. This is a process that takes place slowly, silently, across billions of years. From our human perspective, it feels eternal. But on the scale of galaxies, this kind of interaction is common, normal, even necessary. It's how structures evolve, it's how star systems are reborn, and it's how the universe at every level continues to shape itself without pause. One day, far into the future, the stars of Andromeda and the Milky Way will shine together under a single sky. The shape of that sky will look nothing like the one we know now, but its story will still be written in the same quiet forces that have always ruled the cosmos: mass, motion, time, and gravity, guiding everything, even us, toward new forms that no one alive today will ever see. What black holes really are, simplified, fact-based. A black hole is not a hole. It isn't a tunnel. It isn't a portal. It's a region of space so dense, so heavy, that nothing, not even light, can escape from it. That's why it appears black. Not because it swallows light like a shadow, but because once light crosses a certain boundary, it can't get out. That boundary has a name. It's called the event horizon. And beyond it, everything moves inward, always inward, with no return. Black holes form when enough matter collapses under its own weight. This can happen in different ways, but the most common begins with the death of a star. A massive star burns through its fuel, expands into a red supergiant, and then collapses in on itself in a violent supernova. What's left behind is the core, crushed so tightly by gravity that it forms a singularity, a point of infinite density where our current physics stops being useful. That singularity becomes the center of a black hole. But not all black holes are formed from dying stars. Some are born much larger, millions or even billions of times more massive than our sun. These are called supermassive black holes, and they sit at the center of nearly every large galaxy we've observed. How they form isn't fully understood yet, but their presence is certain. Their gravity influences the orbits of stars around them. Their mass can be measured by how those stars move. And even though we can't see inside them, their fingerprints are everywhere. A black hole isn't an object you can land on. It has no surface, no crust, no shell. As you approach it, gravity becomes more intense, more curved. Space itself begins to warp. Time slows down, and the closer you get to the event horizon, the more extreme that warping becomes. From the outside, it would look like time is freezing for anything approaching the edge. But from within, there's no pause. Once you pass the threshold, you're pulled toward the center. There is no stopping, no turning back. Despite how extreme they are, black holes don't suck things in from a distance like vacuums. If our sun were somehow replaced with a black hole of the exact same mass, Earth would continue orbiting it almost exactly as it does now, just in darkness. Black holes only pull strongly when you get very, very close. Their gravity is intense, but it's not magical. It follows the same rules as everything else. The difference is in the scale. And when something does get close enough, gas, dust, a wandering star, it doesn't just fall straight in, it spirals, it heats up, it forms an accretion disk, a glowing ring of matter circling the black hole, reaching temperatures of millions of degrees. That's where the energy comes from. That's what we can see. The black hole itself is invisible, but what happens around it is anything but quiet. The process of falling in releases enormous amounts of radiation, sometimes more than an entire galaxy of stars, and that energy can be detected from across the universe. There are also smaller black holes, called stellar mass black holes, which range from a few to a few dozen times the mass of our Sun. Some of them are paired with stars in binary systems, and their presence is revealed by how they pull material off their partner. Others are hidden, drifting silently through the galaxy, invisible unless they interact with something. And then there are intermediate black holes, sitting in the middle range of size. Fewer have been found, but they may be the missing link between the small and the supermassive. One of the most striking things about black holes is that they compress space and time around them. In a very real way, they show us how gravity is not just a force, but a warping of reality itself. Light bends near them. Time stretches. Even information behaves differently near their edges. They are not just cosmic objects, they are laboratories, places where the universe's deepest rules reveal their extremes. And yet, for all their complexity, black holes are inevitable. If you gather enough mass in a small enough space, a black hole must form. There's no shortcut around that. It's written into the mathematics of gravity. These aren't rare mistakes or anomalies. They are natural results of how matter behaves when pushed to its limits. To understand black holes is to understand that space isn't flat. It can be curved, it can fold, it can collapse, and in those rare places where it caves in completely, we are left with black holes, silent, cold, and permanent markers of the universe's most dramatic thresholds. Quasar winds from black holes shutting off star formation. At the center of certain galaxies, there's a kind of brightness that defies scale. A glow so powerful it outshines every star in its host galaxy combined. These aren't ordinary stars or clusters, they're quasars, active galactic nuclei powered by supermassive black holes that are feeding aggressively. Not gently, not slowly, but at a pace so intense that the act of consuming creates an eruption of energy on a galactic scale. This feeding isn't quiet. As matter spirals inward toward the event horizon of a black hole, it doesn't vanish immediately. It compresses, heats up, and forms a spinning disk. That disk becomes a furnace, reaching temperatures high enough to emit X-rays, ultraviolet radiation, and visible light in all directions. But the brightness is only part of the story. The real force, the one that changes the future of galaxies, is carried by the wind. These aren't breezes. They are quasar winds, violent outflows of gas and particles launched outward from the accretion disk at tens of thousands of kilometers per second. Some move at a fraction of the speed of light, and as they escape, they sweep through the surrounding galaxy, stripping it of the gas it needs to form new stars. Star formation doesn't die because the fuel runs out slowly. It dies because the fuel is blown away. A galaxy without cold gas is a galaxy that stops growing. Stars are born in dense molecular clouds, regions of low temperature and high pressure where gravity can pull material together. But when a quasar wind cuts through those clouds, it heats the gas, breaks apart the structure, and throws the pieces out into intergalactic space. What was once a nursery becomes a barren field. Entire regions that were once rich with stellar birth go quiet. This process can shut down star formation across an entire galaxy, not just near the core but across distances of tens or even hundreds of thousands of light years. In some galaxies, observations show enormous bubbles and outflows, hollowed-out regions where gas was once dense and active, now replaced by turbulence and heat. These are the scars left by quasar winds, reminders that the black hole at the center is not just pulling material in, it's also pushing it out. The effects of these winds aren't limited to gas. Dust, molecules, even young stars can be caught up in the flow. Some are destroyed, others are flung into eccentric orbits. In some cases, new structures form at the edge of these outflows, dense regions compressed by the shock wave, where stars may briefly bloom before the heat disperses them again. It's a cycle of creation and destruction, moving outward from the most extreme gravitational point in the galaxy. There's also a tipping point. If the black hole is too quiet, the galaxy continues forming stars, growing denser, and feeding its central engine. But if the black hole crosses a threshold, consuming too quickly, it creates a feedback loop. The brighter it shines, the more power it sends outward, and the stronger those winds become, the more they strip away the galaxy's ability to feed the black hole further. It's a delicate balance. Too little energy and growth continues unchecked. Too much, and the galaxy suffocates under the strength of its own core. Over time, this process helps explain why many massive galaxies stop forming stars. They become quiescent, filled with old stars, redder in color, quiet in the infrared. They may still spin, still shine, still hold mass, but inside, they've lost their fire. The fuel is gone, and in many cases the cause can be traced back to a period of intense activity in their center, a time when a supermassive black hole roared at full power, altering everything around it. Quasar winds are not rare. They've been detected in galaxies both near and far, across different epochs of cosmic time. And their signature, broad absorption lines in the light spectrum, patterns of gas velocity, cavities in galactic structure, is consistent. This isn't a theory pinned to a few distant objects. It's a mechanism seen repeatedly across the observable universe. So when we talk about black holes shaping galaxies, it isn't poetic, it's literal. A black hole, by eating too much, can shut down its own galaxy. Not with violence in the traditional sense, but with pressure, radiation, and the quiet, relentless force of energy moving outward. A force that doesn't need to touch a star to silence it. All it needs is to push the sky apart. Black holes as both creators and destroyers of galaxies. There are two stories being told inside every galaxy, one about growth and one about control. And at the center of both is the same figure, a black hole, not always active, not always visible, but always present. It shapes its galaxy not with a single moment of violence, but through a long, subtle tension, balancing the forces that build galaxies with the forces that tear them apart. Black holes are formed from collapse, but their role is far greater than their origin. In their most active state, they feed on surrounding gas, building accretion disks that radiate energy across the electromagnetic spectrum. But what they give off isn't just radiation, it's influence. The material they don't swallow becomes part of powerful winds, broad jets, and heating events that alter the chemistry of their galaxy's heart. And yet, even as they prevent new stars from forming in some places, they provoke it in others. When a black hole sends shockwaves through surrounding gas, it doesn't always shut down growth. In certain conditions, those shockwaves compress matter, driving the gas to collapse and spark new starbirth. These pockets of triggered formation create bursts of light in regions that would have otherwise remained dormant. It's an indirect hand, a kind of sculptor's pressure, shaping clouds not by pulling them, but by pushing just hard enough to fold them inward. In this way, black holes become catalysts. They also act as gatekeepers. In the early universe, galaxies grew rapidly. Gas was abundant. Star formation ran hot and fast. But unchecked, this would have led to unstable systems. Too massive, too chaotic, too fast-burning to hold their shape. Black holes, by regulating that growth, helped structure the process. They limited starburst events. They created cycles. periods of activity followed by periods of calm, allowing galaxies to evolve steadily over billions of years. At the same time, the very same black holes that helped stabilize early galaxies have the power to end their star-forming lives. When they become too active, they sweep away gas and dust. They overheat the medium, they eject material into intergalactic space. What was once a system of growing clusters becomes a graveyard of red, aging stars. The galaxy doesn't collapse, it freezes in time. Evolution slows, growth stops. Not through destruction, but through deprivation. This duality, creation and suppression, isn't theoretical. It's observed in the galaxies themselves. The most massive galaxies in the universe often host the largest central black holes, and these galaxies show evidence of both intense early growth and long-term quiet. Their outer halos glow with the light of ancient stars. Their cores often pulse with the faint remnants of powerful jets or the heat of long-dead accretion events. What we see is the memory of balance. Too much energy and the galaxy dries up. Too little, and it collapses into chaos. In merging galaxies, the role becomes even more complex. When two galaxies collide, their black holes eventually spiral toward each other. The gas compressed during the collision lights up with new star formation, while the black holes may remain dormant at first, hidden in the chaos. But as the merger settles, their influence grows. The central regions compress. Activity ignites. A new phase begins. And as the two black holes eventually merge, they send out gravitational waves that ripple through the very fabric of space. Even after death, their impact lingers. Some galaxies now show signs of black holes that no longer actively feed. Yet the after effects are still written across the structure. Disrupted gas lanes, ejected material, inactive star-forming regions. Like a long-extinguished fire, the environment still bears the heat. Their memory persists, even in silence. So the question is no longer whether black holes are creators or destroyers. The answer is both. They don't choose. They respond to their environment, to mass, to momentum. Their influence can preserve or erase, feed or starve, depending on how they interact with the matter around them. And through that, they become something more than cosmic anomalies. They become organizers, editors, shapers of everything large-scale structure depends on. Galaxies are not passive shells with black holes in their center. They are systems built around them. Systems that rise and fall, burn and rest, grow and decay, depending on the rhythm set by a singular point of collapse that never releases what it holds. And through that grip, dark, invisible, relentless, entire galaxies are born, shaped, quieted, and remade. Not with explosions, but with gravity. Not with purpose, but with presence. Black holes do not direct the orchestra, but they set the key. Filaments, the threads of galaxies, forming the universe's shape. Galaxies do not drift randomly through space. They follow paths, long, interconnected lines that stretch across the cosmos like veins beneath the skin of the universe. These are filaments, the largest visible structures known to exist. Not made of stars alone, but of galaxies, millions of them, threaded together in sprawling bridges of light and matter that connect everything we can see to everything we can't. If you zoom out far enough, the universe doesn't look chaotic. It looks like a pattern. Galaxies are arranged along lines and curves, creating something that resembles a giant three-dimensional web. These filaments are not simply visual tricks. They are real structures, shaped by gravity over billions of years, and they extend across hundreds of millions of light years. They are the scaffolding upon which galaxies form, evolve, and move. Without them, there would be no structure to the universe at all. Each filament is formed from a combination of dark matter, gas, and galaxies. Dark matter provides the invisible mass, the deep gravitational wells that pull regular matter into shape. Over time, this matter gathers into narrow lanes, where gas cools, condenses, and gives rise to stars and galaxies. The galaxies then become the visible part, the glowing markers that trace the filament's paths like lanterns hanging on a hidden frame. But these structures didn't appear all at once. In the earliest moments of the universe, matter was nearly evenly spread. Over time, slight variations in density, tiny fluctuations in temperature and energy began to grow. The denser regions pulled in more matter, and the empty ones gave it up. Slowly, what was once a smooth field broke apart into threads and knots. The threads became filaments. The knots became galaxy clusters, and the spaces between them grew into vast cosmic voids. Even now, the filaments continue to evolve. Gravity still pulls galaxies toward the densest intersections. These crossroads, where multiple filaments meet, are home to the most massive clusters we've ever observed. But the filaments themselves are not empty highways. They contain their own populations of galaxies, smaller, quieter, often stretched in shape, moving along the flow of gravity like leaves in a river. The distances involved are staggering. A single filament can stretch hundreds of millions of light years from end to end. Some are relatively straight, others twist and curve, but together they form a network that fills the entire observable universe. Every galaxy belongs to this network. Every star, every system. There is no such thing as isolation in this design. Everything is connected, physically and gravitationally, through a system we're only beginning to fully map. Even more impressive is that these filaments serve as cosmic pipelines. Gas flows along them from one region to another, feeding galaxies and fueling star formation. Some galaxies at the ends of filaments are actively growing, pulling in fresh material from their surroundings. Others, located farther from these roots, age more quickly, cut off from the resources they need to build. The position of a galaxy within the web can determine its lifespan, its shape, and even the rate at which it forms stars. In between the filaments lie the voids, regions so empty they contain almost nothing at all. These contrasting zones of structure and silence make the cosmic web even more distinct. The filaments are not scattered randomly. They are separated by spaces that span tens of millions of light years, and those gaps amplify the structure, highlighting the depth of the web with every survey we complete. What makes all of this more profound is that the cosmic web is not static. It shifts. Slowly, the filaments grow thicker as more matter falls into them. The clusters at the intersections grow heavier. Galaxies migrate along the filaments, drawn by gravity, their motion subtle but measurable. Over billions of years, this movement reshapes the web, even as it preserves its overall design. To see a map of the cosmic web is to see the handwriting of gravity on the largest possible scale. It is the story of how matter organizes itself when left alone with time and force. No symmetry was imposed, no architect drew the lines, and yet a structure emerged. Order from fluctuation, pattern from randomness, a universe that arranges itself not because it must, but because gravity gives it the freedom to do so. And through those filaments we see not just where galaxies are, but how they are connected by invisible lines of force that stretch across billions of years. These are not paths we travel. They are the paths that made us, the frame into which everything else was set, the threads that stitched a universe together and still hold it in shape, light by light, star by star. Galaxy superclusters and walls, e.g., Sloan Great Wall. There are structures in the universe so massive, so far beyond anything we can build, that they don't just redefine scale, they erase it. One of those structures is the galaxy supercluster. These are not galaxies, not even clusters of galaxies. They are collections of clusters, bound loosely by gravity and arranged in formations that stretch across hundreds of millions of light years. They are the largest known organized groupings of matter in the observable universe. Superclusters don't exist on their own. They are part of the cosmic web, formed at the densest intersections of filaments, those long threads of galaxies and gas that define the layout of space. Where several filaments converge, gravity acts more strongly, pulling in more mass, gathering more galaxies and weaving them into structures that go far beyond individual identity. These gatherings take on complex shapes, curved, uneven, sometimes arc-like, sometimes wall-like, and their total scale is staggering. Take the Sloan Great Wall, for example. First detected in 2003, it spans over 1.4 billion light-years. It isn't a single object. It's a series of galaxy clusters and smaller walls arranged into a vast, coherent formation. If you could somehow view it all at once, it would resemble a wall of light and matter, frozen in shape by the combined gravity of everything within it. It's not just large, it's structural. It defines the boundary between major voids and denser regions of the universe, and it's only one among many. There are others: the Hercules Corona Borealis Great Wall, the CFA2 Great Wall, Laniakea, which includes our own local group, and together they form an architecture we were never meant to see from the inside. And yet, here we are, mapping them with instruments sensitive enough to measure the redshift of galaxies over billions of years. Each new wall or supercluster discovery pushes the limits of how we understand large-scale structure. Within these superclusters, galaxies are not evenly spaced. There are rivers of galaxies, called filaments, and wide flat zones packed with clusters, like sheets of stars stacked across space. These dense regions interact with their surroundings. Their gravitational pull can alter the movement of smaller clusters and affect the direction of entire galactic flows. The movement isn't rapid. It happens over billions of years, but the direction is clear. Matter flows toward mass, and the biggest concentrations of mass are always found inside these vast walls. Even though they appear frozen in space, superclusters are dynamic. Their components move, drift, and fall toward gravitational centers. Some clusters will merge. Some galaxies will change direction. Others may even fall into vast attractors, enormous unseen regions of gravity that tug on everything around them. In this way, the walls and superclusters are more like scaffolds in motion. Their overall shape may persist, but their interiors shift, reorganize, and evolve slowly over cosmic time. They also create boundaries, not physical walls you can touch, but transitional zones in the universe's layout. On one side of a supercluster wall, galaxies might be densely packed, rich in gas, full of active star formation. Just beyond it, there might be an enormous void, a region so empty it's almost entirely dark, except for a scattered few galaxies drifting in isolation. These boundaries help define the skeleton of the cosmos, separating spaces of light from spaces of silence. The presence of these massive structures challenges the idea of uniformity on large scales. For decades, cosmology operated on the principle that, when viewed broadly enough, the universe should be homogeneous, the same in every direction. But walls like Sloan and Laniakea suggest that structure persists at far greater scales than we expected. It doesn't break the laws of physics, but it forces us to ask whether the early seeds of density that shaped these structures were more complex than once thought. And it's not just about shape, it's about influence. Superclusters may have played a major role in how galaxies evolved within them. Galaxies that grow in dense environments tend to interact more often, merging, stripping each other of gas, quenching star formation earlier than isolated galaxies. Over time, this affects the color, age, and activity of the galaxies that remain. So, in a very real way, a galaxy's life can be shaped by its position inside or outside of a wall. All of this, the walls, the clusters, the vast scales, is invisible to the eye. These structures can't be seen in a single photograph. They can only be revealed through surveys that scan deep into space, layer by layer, compiling positions, distances, and velocities. And when those data are plotted, the shapes emerge, not randomly, but with rhythm, with connection, with coherence. So when we speak of galaxy walls and superclusters, we are not describing scattered islands. We're describing continent-sized patterns spread across the universe, defining where matter lives, where it migrates, and where it falls silent. These aren't remnants of something past. They are the living bones of the present cosmos, still shifting, still binding, still carrying the weight of structure across a universe in motion. The Big Ring, a formation that defies current understanding. There are discoveries that extend what we know. Then there are those that break the shape of our expectations. The Big Ring belongs to the second category. Found not through theory, but through observation, it is a structure so vast, so unlike anything mapped before, that it resists explanation, not just in detail, but in principle. It isn't a wall, a cluster, or a filament. It's not part of the familiar cosmic web as we've come to understand it. The Big Ring is a massive, ring-shaped arrangement of galaxies, about 1.3 billion light-years wide, located roughly 9.2 billion light-years from Earth. At that distance, we're looking at a time when the universe was only a third of its current age. And yet, even then, this formation was already in place, completed, coordinated, and stable. The galaxies forming this ring are not orbiting one another. They're not bound in a circular gravitational dance. The distances between them are too vast for such movement. Instead, they lie positioned along an enormous loop-like structure, as if outlining a hole in space too large to define. It isn't a shape left behind by collapse, nor a ripple from a known process. It's a structure that shouldn't exist, not at this scale, not in this form. According to what we understand about large-scale structure formation, the universe is supposed to be statistically isotropic, appearing the same in every direction when viewed on large enough scales. That rule has held for decades. But formations like the Big Ring start to strain that assumption. Their symmetry is too clean, their presence too isolated, their alignment too deliberate. The pattern they create can't be easily dismissed as coincidence, yet it doesn't follow any of the formation models that explain filaments or walls. What makes the Big Ring more intriguing is how it challenges the expected limits of structure. Cosmologists generally agree there's a horizon, a maximum scale at which cosmic structures can remain causally connected by the age and expansion of the universe. The Big Ring exceeds that scale. Its diameter is so wide that its edges could not have exchanged information since the Big Bang, meaning it couldn't have formed from a shared physical cause, at least not with the processes we currently understand. The galaxies within the ring are also unusual in their redshift alignment, showing signs of similar age and motion. This coherence implies a shared history, or a simultaneous disturbance. But again, the mechanism that could lead to such coordination over this scale has no clear candidate. No nearby mass concentrations. No lensing anomalies. No apparent distortions in the cosmic microwave background that might hint at a local warp or inflationary residue. It's as if the ring was stamped there, imposed rather than evolved. Some have suggested that the Big Ring may be the remnant of a topological defect in space-time, a kind of scar left over from the early universe where symmetry broke down in a non-uniform way. Others speculate it might be an echo from a different dimension of space, or a statistical outlier amplified by selection bias. But none of those answers rest comfortably in current frameworks. They require bending the laws of physics or extending models into territories that are untested and, for now, unreachable. What's clear is that the Big Ring has massive implications, not just for how we view the structure of the universe, but for how we model the conditions that produced it. If this formation is real, and the data so far strongly supports it, then there may be processes at work in the cosmos that are older, deeper, and stranger than our current theories can support. Processes that aren't visible through radiation or matter, but only through the shapes they leave behind. The existence of the Big Ring also raises the question of whether it's unique. Is it a singular anomaly, or are there other rings hidden deeper in the universe? Too faint, too far, or too complex to detect with current instruments? And if there are more, do they follow a pattern? A hidden geometry that threads through the observable cosmos, hinting at a structure beneath the web we thought we understood. Even without full answers, the Big Ring forces us to reconsider how we define cosmic structure. It tells us that the universe may not just stretch outward. It may curve, spiral, or fold in ways we've never accounted for. It suggests that there could be symmetry, not just in clustering, but in emptiness. That absence itself may arrange into patterns with meaning. No one predicted this. No one modeled it. And yet the Big Ring remains, a silent loop of galaxies, too large to ignore, too perfect to dismiss. It may be an accident of light and distance. Or it may be the first sign of a larger architecture we've yet to decipher. Whatever it is, it stands as a quiet contradiction to everything expected. An open question written in galaxies, curved across 1 billion light-years, waiting for someone to understand what it really means. Void regions versus densely packed areas. The universe is not evenly filled. It is a landscape of contrast. There are places where galaxies cluster so tightly they stretch into chains, sheets, and walls, regions where gravity gathers matter into visible complexity. And then, surrounding those clusters, there are vast open stretches of almost nothing. These are the voids, immense regions of low density where galaxies are scarce, and light itself feels distant. Voids are not small. The average void spans tens to hundreds of millions of light-years across. Some are so large that entire superclusters could vanish inside them without touching a single wall. They are not empty in the strictest sense, but compared to the cosmic filaments and walls, they are barren. A single galaxy drifting through a void can be separated from its nearest neighbor by tens of millions of light-years, isolated in both space and time. What defines a void is not the total absence of matter, but the lack of structure. These are places where gravitational pull has emptied out the volume. In the early universe, tiny fluctuations in density began to grow. Dense regions pulled in more mass, while less dense regions were evacuated. Over billions of years, this led to a sharpening of contrast. Clusters grew thicker, and voids grew deeper. The matter wasn't destroyed, it just moved somewhere else. In the denser zones, galaxies form in abundance. Gas compresses into filaments. Stars are born rapidly. Mergers happen frequently. The gravitational complexity increases with every interaction, leading to intricate structures. Superclusters, galaxy groups, massive elliptical galaxies. These zones are hot, Both in energy and activity, they evolve quickly and visibly. In voids, the opposite happens. The scarcity of matter means fewer gravitational interactions. Fewer galaxies form. The ones that do are often smaller, irregular, and less chemically evolved. Star formation is slower, less frequent, and more sensitive to outside disturbance. Some galaxies and voids may have gone untouched for billions of years, never merging, never disturbed, drifting silently through a darkness far more permanent than anything near a filament. Galaxies in these contrasting environments live very different lives. In clusters, they compete for resources. They experience tidal forces, gravitational harassment, gas stripping, and high-speed collisions. Their shapes are molded by pressure. Their growth is regulated by how well they can hold on to fuel in the presence of neighbors. In voids, galaxies are often left alone. They evolve in relative peace, shaped more by their internal processes than by external collisions. Some of them retain gas reservoirs for much longer, allowing prolonged star formation. Others remain faint, dim, and sparse, starving not because of interaction, but from a lack of opportunity. The boundaries between voids and dense regions are sometimes abrupt. A single galaxy can lie near the edge, influenced by both the silence behind and the pull ahead. These edge galaxies act like sentinels, bridge points between emptiness and activity, subject to forces from both sides. Over time, even they can be drawn outward, slipping into the filaments, becoming part of the growing structure as gravity continues its slow rearrangement. Void regions also help define the true scale of the universe. It's not just about what is present, but what is missing. The space between tells a story just as important as the galaxies themselves. By studying the emptiness, cosmologists can refine models of how matter behaves, how structure forms, and how dark energy influences expansion. Even the shape and size of voids leave clues about the nature of the universe's earliest conditions. Some of the largest known voids, such as the Bhuta's void, are so empty they challenge our expectations. The Bhuta's void alone spans over 300 million light-years and contains far fewer galaxies than predicted by statistical averages. Its emptiness forces a reconsideration of how random early fluctuations might have been. Whether such a void is an anomaly or part of a larger pattern still being uncovered remains a topic of deep exploration. But perhaps the most profound truth about voids is how they reveal the architecture of a contrast. The universe is not a canvas painted evenly. It is defined by tension, between pull and release, matter and absence, noise and silence. Galaxies light the sky not alone, but because of where they are not. The space between them frames the shape of everything. This interplay between void and structure is ongoing. As time progresses, the gravitational dominance of dense areas continues to grow. Voids slowly evacuate more matter. Clusters become more compact. The expansion of space only widens the contrast. What is dense becomes denser. What is empty becomes more empty. The pattern sharpens with age. So, when we look at the night sky and wonder about the galaxies we see, we should also wonder about the darkness that surrounds them. Not as background, not as filler, but as part of the story. The silence between the galaxies is not empty of meaning. It is the frame that makes the structure visible. And in that silence, the shape of the universe is being stretched, quietly, constantly, and completely. How stars are born from gas and dust, the interstellar medium. In between the stars, there's more than darkness. There's material, thin, scattered, cold, but present. Stretching between stellar systems and across galactic arms, this substance, made of gas, dust, and trace elements, is known as the interstellar medium. It may appear empty, but this is where stars begin. Every glowing point in the sky started from this invisible sea, from particles so faint that across a cubic meter of space, you might find just a handful of atoms. The interstellar medium is not uniform. It contains vast differences in temperature, pressure, and composition. Most of it is hydrogen, the universe's simplest and most abundant element, accompanied by helium, carbon, oxygen, and grains of dust made from heavier materials. These ingredients drift in clouds that span light years, sometimes so cold they hover just a few degrees above absolute zero. Within these clouds, molecular regions form, places dense and cool enough for atoms to bond into molecules. Here, the gas slows, dust gathers, and gravity starts to whisper. A region that was once floating silently becomes heavy. Subtle motions begin, pressures shift, and deep within, the first hints of collapse begin to take shape. This collapse doesn't happen instantly. It starts in the core of the densest parts of the cloud, where the gravitational pull becomes strong enough to overcome outward pressure. Over time, the gas and dust fall inward, compressing further. As the material packs tighter, friction increases and the temperature rises. What begins as a slow drift becomes an inward plunge, centered on a point that now holds more mass than the space around it. Inside this collapsing core, pressure and heat build continuously. Dust grains collide, stick, and begin to melt into larger particles. Molecules break apart under rising temperatures, and the infalling gas starts to glow faintly, not from fusion, but from compression. This object, not yet a star, becomes what's called a protostar, a hot, dense clump hidden within the original cloud. Around the protostar, a disk of leftover material begins to flatten and swirl, shaped by angular momentum. Some of this material will fall inward, feeding the core. Some will clump together, forming planets, moons, asteroids. But the core remains the focus. It grows hotter with every heartbeat of gravity, reaching millions of degrees. Deep within, atoms begin to collide fast enough for nuclear fusion to begin, the point where hydrogen nuclei start fusing into helium. That moment marks a turning point. When the pressure from fusion equals the gravitational pull inward, the collapse halts. Balance is reached, and a star is born. But not every cloud leads to light. In many regions, the interstellar medium remains too thin or too warm to collapse. Supernovae, exploding stars, can sweep through and stir things up, compressing gas enough to start the process. Collisions between clouds can trigger it as well. Even pressure from spiral arms in a galaxy can cause clouds to compress, leading to clusters of stars born in sequence, shaped by a wave of gravitational disturbance. Inside the densest birthplaces, stars form in groups. These stellar nurseries can host hundreds or thousands of new stars, many still wrapped in the dust that formed them. Over time, radiation from the most massive among them clears out the surrounding gas, blowing bubbles into the medium and sometimes cutting off further star formation in nearby regions. The interstellar medium is constantly recycled. When stars die, especially in supernovae, they return enriched materials, carbon, oxygen, silicon, back into the space between stars. This material mixes with older gas, seeding the next generation of stars with heavier elements. With every cycle, the chemistry of the galaxy evolves. The stars born today carry more complex ingredients than the first stars ever did, and that complexity extends outward to planets, atmospheres, and eventually the potential for life. Some parts of the interstellar medium are filled with ionized gas, glowing softly in specific wavelengths. Others remain dark, invisible without specialized instruments. There are cold, dense clouds called Bok globules, dark silhouettes against brighter backgrounds, where stars may be forming in secret. And there are giant molecular complexes spanning hundreds of light years, where entire clusters can emerge over time. Even though it seems empty, the interstellar medium is active. It breathes, reshapes, collapses, expands. It carries the echoes of dying stars and the seeds of those yet to ignite. It is not a gap between things, it is the process itself. The space that builds the stars, sculpts galaxies, and keeps the universe from falling into silence. Every star that ever lived started in a place like this, a quiet region, unnoticed, slowly shifting toward collapse. From that collapse comes heat, from heat comes fusion, and from fusion light. And so, what begins in darkness ends in radiance. Not quickly, not easily, but through a long conversation between matter and gravity, told in particles drifting across the oldest and quietest places in space. Life cycles of stars, from cloud to collapse. Every star is temporary. From its first breath of fusion to its final flicker, it follows a path shaped entirely by mass, pressure, temperature, and time. The life of a star does not move quickly, but it is never still. And from the moment a dense knot of gas begins to collapse, a countdown begins, one that can last millions, billions, or even trillions of years. The story begins in a cold region of space, deep within a molecular cloud. A disturbance, sometimes a shock wave, sometimes a nearby gravitational tug, triggers a section of this cloud to collapse inward. It doesn't fall cleanly, it fragments. Pockets of matter compress independently, each with the potential to become a star. These fragments deepen, pulling in more gas, heating at the center. The denser they become, the more unstoppable the collapse becomes. Eventually, a protostar forms, hot, dense, spinning. But it is not yet a star. Its core must reach the ignition point for hydrogen fusion, the process that transforms hydrogen into helium, releasing energy that pushes back against gravity. When this fusion stabilizes, the protostar enters a long, steady phase. It becomes a main sequence star, and this stage can last for the majority of its lifetime. The length of time a star remains in this phase depends on its mass. Small stars burn slowly. Their fusion rates are low, their luminosity gentle. They can shine for trillions of years, far longer than the current age of the universe. Medium stars, like our Sun, burn hotter, faster. Their lives stretch over billions of years, and massive stars, those 10, 20 or more times the Sun's mass, live fast, burn violently, and die young. Some last just a few million years before reaching their end. As the star consumes hydrogen in its core, it begins to change. Eventually, the core is depleted of its primary fuel. Fusion slows. Gravity begins to win again, compressing the core. But this compression triggers a new reaction. Hydrogen shell burning, where fusion begins in a shell surrounding the inert core. The outer layers of the star expand outward, sometimes dramatically, transforming it into a red giant or red supergiant, depending on its original size. For medium-sized stars, this red giant phase marks a gentle but inevitable decline. The core compresses until helium fusion ignites, converting helium into heavier elements like carbon and oxygen. But this phase cannot last. Once helium is exhausted, fusion halts again. The star sheds its outer layers into space, forming a glowing planetary nebula, while the core contracts into a white dwarf. A small, dense remnant that no longer undergoes fusion but still glows from residual heat. This white dwarf may remain unchanged for billions of years, slowly cooling until it becomes a black dwarf. a theoretical object, since the universe isn't old enough for any to exist yet. These remnants are incredibly dense, packing the mass of a star into the size of a planet, and incredibly quiet. They no longer produce light, but they remain, drifting through space, undisturbed and unchanging. For massive stars, the path is far more violent. Their cores are hot enough to fuse elements beyond helium, carbon, neon, oxygen, all the way up to iron. But iron is the end. It doesn't release energy when fused, it absorbs it. Once a star's core is mostly iron, fusion stops. The pressure that held back gravity disappears. The core collapses inward in a matter of seconds. What follows is one of the most dramatic events in the universe: a supernova. The outer layers are blasted into space in a burst of light and energy, briefly outshining entire galaxies. In that explosion, elements heavier than iron, gold, uranium, platinum, are forged and thrown across space. These are the building blocks of planets, moons, even life. What remains of the star depends on its mass. If it's below a certain threshold, the core stabilizes as a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. But if the mass exceeds that limit, the collapse continues. Gravity crushes the core into a black hole, an object with no surface, no escape, no way for light or matter to return. It doesn't end in fire, but in silence. And yet, even in this silence, its presence shapes space for eternity. Stars do not die alone. Their remnants shape everything around them. Their light seeds planets with warmth. Their death spreads elements across galaxies. Their collapse creates gravitational waves. They recycle matter. They set the pace of galactic evolution. Even long after they disappear, their fingerprints remain, in dust, in light, in atoms embedded in your own blood. The life of a star is not a simple arc, it's a process of transformation, a cycle of pressure, energy, balance, and collapse. It begins in darkness, shines for eons, and ends in a form more compact and extreme than the beginning could ever predict. But through that journey, the universe becomes more structured, more complex, more capable of giving rise to new light, new worlds, and everything we have come to know. The Milky Way's future: merger with Andromeda into Milkomeda. The stars in our sky look fixed, anchored to the heavens, but everything is moving. Every galaxy is on a path set by gravity and time, and our home, the Milky Way, is no exception. It is drifting through space with quiet force, carrying every planet, every star, every memory of Earth, toward a collision that has already begun unfolding on a cosmic scale. Roughly 2.5 million light-years away, the Andromeda Galaxy is approaching. It is massive, spiral-shaped like our own, with a disk filled with billions of stars, clusters, and gas clouds. And although the space between us and Andromeda is vast, the distance shrinks each year by about 110 kilometers per second. This motion isn't a fluke. It's gravitational inevitability. The two galaxies are falling toward one another in slow motion, guided by the mutual pull of their combined mass. The collision won't be a violent smash in the way it sounds. Galaxies are mostly empty space. Stars are separated by such incredible distances that they rarely, if ever, collide directly. Instead, the merger will unfold as a long, gravitational dance, one that will stretch over billions of years. The first pass will distort both galaxies, drawing out long tidal tails of stars and gas, flinging them into intergalactic space. Spiral arms will twist and warp. Cores will stretch, and each galaxy will pull material from the other, reshaping their structures with every encounter. After the first pass, they won't settle immediately. Like dancers crossing paths and circling back, the two galaxies will pass through each other multiple times. Each interaction will stretch, compress, and rearrange their stars. Great waves of new star formation will flare up as gas clouds collide and compress, igniting bright bursts of activity. But over time, the raw material for forming stars will dwindle, and when the dust begins to settle, literally and cosmically, what remains will no longer resemble either of the original galaxies. Instead, the Milky Way and Andromeda will fuse into a single, massive elliptical galaxy. It won't have the delicate spiral arms of its predecessors. It will be rounder, smoother, older. Its rotation will be slower. Its bright core will swell from the merger of two central black holes, ours and Andromeda's, spiraling toward one another until they finally become one. That black hole, now significantly larger, will anchor the center of the new galaxy. This future galaxy already has a name, Milkomeda. It will be larger than either of its parents, more massive. Its halo of stars will be thicker. Its central bulge will glow with ancient light. Many of the stars visible from Earth today will be carried into new orbits, shifted far from their original positions. The solar system, if it still exists by then, will not be destroyed, but its place in the sky will be unrecognizable. Our view of the night will shift from the broad river of the Milky Way to a soft, golden haze, a more uniform glow from the core of a settled, mature galaxy. The merger will also pull in other galaxies from our local group. Smaller galaxies like Triangulum, and many of the dwarf companions of both the Milky Way and Andromeda will be caught up in the same gravitational reshuffling. In time, they too will be absorbed into Milkomeda, expanding its size, contributing their stars, and disappearing as independent structures. But even as the galaxies collide, there will be no chaos from a local, planetary perspective. The solar system won't be shaken apart. Earth won't suddenly be dragged out of orbit. The scale is too vast, and the density too low. What will change is the cosmic environment, the backdrop of stars, the patterns of movement, the structure of everything beyond our sun. The constellations we know will be erased, replaced by new, unfamiliar shapes born from the merger. As Milkomeda forms, the surrounding void will grow. Over time, the expansion of the universe will carry other galaxy groups far beyond our reach. Milkomeda may become increasingly isolated. The light from galaxies outside our local supercluster will eventually stretch beyond visibility, leaving Milkomeda as one of the last major structures we can study from within. Future civilizations, if any remain, may no longer see a universe filled with countless galaxies. They may only see their own. But within that new galaxy, the legacy of the Milky Way will persist. Its stars, its black hole, its planetary systems will remain embedded in a new whole. No longer a distinct spiral, but a contributor to something larger. The formation of Milkomeda will not be the end of galactic evolution, but one more chapter in the process of reshaping structure through gravity and motion. Galaxies live long lives. They are built slowly and changed by encounters that take longer than entire species survive. But they do change. They merge, evolve, brighten, fade. And in that slow exchange, they tell the story of the universe's structure, built not in stillness but in movement. The Milky Way is not permanent. It is a phase, one part of a larger journey, a snapshot in a process still unfolding, quietly, across space too vast for our lifetimes to grasp, yet close enough to belong to our future. Distant future, when star formation stops and the sky goes dark. The sky has always offered light. Every night stars scatter across the black, some near, some impossibly far, all burning with energy that began long before we were born. But that light won't last forever. There is a future where the sky will fade. Not suddenly, not loudly, but through a long, unstoppable quieting. A time will come when the universe runs out of stars to form. A time when the night becomes more than dark. It becomes empty. The reason is simple. Fuel. Every star is born from gas. Cold hydrogen collapsing under its own weight, sparked into fusion. But that gas is limited. Every generation of stars consumes more of it. When massive stars explode, some of that material is recycled. But with each cycle, more is locked into dead remnants, white dwarfs, neutron stars, black holes. And once gas falls into those end states, it doesn't return. Right now, the universe is still forming stars. Not as fast as before, but enough to keep the galaxies glowing. New stars are born in nurseries scattered across spiral arms, in the hearts of gas-rich galaxies, in faint corners just warming to life. But this activity is slowing. Star formation peaked billions of years ago. Since then, the pace has dropped steadily. There's less cold gas. More stars are dying than forming. The balance is shifting, fast forward. Tens of billions of years from now, most of the hydrogen suitable for star formation will be gone. Galaxies will continue to drift apart, stretching the distances between them until light from neighboring groups becomes unreachable. Gravity will still hold some structures together, clusters, merged galaxies, but they will no longer be bright with new stars. Instead, they will be filled with the long-burning remnants of an earlier age. The last stars to form will not be massive giants. Those burn through fuel too quickly. Instead, the final generation will be red dwarfs, small, cool stars with lifespans that stretch for trillions of years. They burn slowly, using their fuel with patience. They don't flare with brilliance, but they endure. And as other stars fade away, these red dwarfs will become the dominant light in the sky. Soft, reddish, and few. Eventually, even the red dwarfs will run out of fuel. They won't explode. They'll shrink, cool, and fade into black dwarfs, cold, dead remnants, no longer emitting light. They will be nearly invisible, but still massive. They will float in silence, stellar corpses that never left their orbit, dimmed entirely, their energy exhausted. By this time, the universe will have become a gallery of remains. The visible stars will be gone. Left behind will be a population of collapsed objects, white dwarfs, neutron stars, black holes. No fusion, no radiation, just the gravitational echoes of what once was. Occasionally, these remnants may collide. Two white dwarfs may spiral together, creating a brief burst of energy. A rogue black hole may consume a passing star, but these will be rare, short-lived flickers in a cosmos grown quiet. Temperature across the universe will continue to fall. Background radiation, once the bright afterglow of the Big Bang, will stretch further, growing colder, less energetic, until it becomes effectively undetectable. Space will cool toward absolute zero, a place without heat, without motion, without light. Galaxies that once formed stars by the billions will now contain none. Only cold relics. Their shapes will persist for a while, but they will stop evolving. Motion will continue, but creation will not. The cosmic web that once carried gas between filaments will collapse inward, drained of purpose. The universe will not reverse or collapse into a new beginning. It will coast, carried endlessly by its own expansion. Over unimaginable time, even the most stable objects will break down. Protons, the particles that make up atoms, may decay, depending on physics still being tested. If they do, every solid structure will dissolve. Planets, moons, even the black dwarfs. Everything that once held shape will drift apart at the subatomic level. And if protons are stable, then the universe will still lose energy through gravitational radiation and quantum decay. Just slower, but always forward. Black holes, the last great anchors of structure, will take the longest to fade. But even they aren't immune. Through a process called Hawking radiation, they will slowly lose mass, particle by particle. The smaller they become, the faster they evaporate. Eventually, even the largest supermassive black holes will vanish, leaving no trace, no object, no glow, no horizon. Only space stretched flat. This era, sometimes called the degenerate era, sometimes the dark era, will last longer than all of cosmic history combined. Time will still exist. Movement will still occur. But without structure, without light, the universe will become a place without observers. No planets to orbit stars. No stars to shape galaxies. No galaxies to hold structure. Only an endless, cold expanse, aging without evidence. But even in that far-off silence, the story remains extraordinary. The universe began hot, bright, and full of potential. It built stars, planets, and people. It created light from emptiness, structure from chaos. And though that light will one day fade, the record of its existence is written in everything that remains. Nothing lasts forever, not even the stars. But the fact that they shone at all, that they were born, lived, and gave light to the darkness, is the reason anything in the universe was ever visible to begin with. And though the future may belong to silence, the present still belongs to light. Stillness at the edge of the cosmos. There are stories that unfold with noise, and then there are the ones that finish in silence. What you've just heard wasn't meant to explain everything. It was meant to leave space for wonder, for stillness, for the simple awareness that you're part of something too wide to measure, too old to remember, and still continuing. Not every mystery needs solving. Some are meant to soften the world around you, to remind you that even in the stillest corners of the universe, something is always shifting. Quietly, slowly, beyond the reach of our senses, yet somehow still reaching us. Right now, your heartbeat moves in rhythm with time shaped by stars you'll never meet. The atoms in your body trace back to supernovae that lit up long-collapsed galaxies. You're not just in the universe. You are what it made. Layer by layer, breath by breath. Built from particles that drifted through space for billions of years before ever knowing purpose. It's not the answers that stay with us. It's the scale, the texture, the feeling of standing next to something vast and knowing. It doesn't require your understanding to keep going. Galaxies will merge, stars will die, and the quiet between them will grow wider. And yet, there is peace in knowing it's not a mistake. It's a rhythm. Even the smallest thought, the quietest realization, travels through your mind like a ripple in that rhythm. You don't need to reach across light years to feel it. You're already folded into it. Everything you are is still in motion, no matter how still you become. So rest now, not because there's nothing left to ask, but because this story doesn't need to be finished to be complete. Let your thoughts slow. Let the scale fade. Let the pace of the universe carry your breath a little further from worry, a little closer to weightlessness. And know this. Right now, passing silently through your body, are relics of the oldest light in the universe. Photons born just 380,000 years after the Big Bang. They've been traveling for nearly 14 billion years without stopping. Not once. And they've just now, only now, reached you. You don't have to chase the stars to be near them. They never stopped arriving.